In this video, we're going to study center of mass. So this will be broken down into three broad categories: a point mass system along an axis, point mass system in the plane, so a two-dimensional coordinate system, and then the center of mass of a lamina. So let's consider point masses along an axis. So start with a long, thin wire of negligible mass resting along a fulcrum. All right. Then what we're going to do is let's put mass, an object of mass, call it M1. Let's draw that bigger. On one side, an object of mass M2 on the other. All right. Obviously, right, we have the fulcrum. Mass M1 is going to have some distance, call it D1, from the fulcrum. Mass M2 is going to have some distance, call it D2, from the fulcrum. So most common real-life example of a system such as this is a playground seesaw, right, with children of different weights. Right now, on a seesaw, if one child sits at each end, the heavier child sinks down, right, and the lighter child is lifted up. If the heavier child slides in towards the center, though, the seesaw will then begin to balance. Now we apply this to our situation here. And we note that the system is balanced if and only if M1 D1 is equal to M2 times D2. If we label positions of M1 and M2 as X1 and X2 respectively, and we label the center of mass, which I'm going to shorthand as COM, as X bar, then the equation becomes M1 X bar minus X1 is equal to M2 times X bar minus X2. I'm sorry, X2 minus X bar. All right, distribute the masses through. Obviously, our goal here is to solve for X bar. All right, so this is what we get. So x bar would be m1x1 plus m2x2 divided by m1 plus m2. So the expression in the numerator, this m1x1 plus m2x2, is referred to as the moment of the system. Obviously, m1 plus m2 is total mass. So center of mass is the moment divided by total mass of the system. Now, this concept can be extended to n bodies. Right? So in general, again, the center of mass is equal to the moment of the system divided by total mass of system. Mathematically, we get x bar is equal to the summation I equals 1 to n, m sub I times x sub I, all over summation I equals 1 to n of m sub I. As an example, what we're going to do is we're going to consider masses. M1 is 30 kilograms. M2 is 5 kilograms. M3 is 10 kilograms. And M4 is 15 kilograms. Right? We're going to be located at x1 equals -2 meters. x2 equals 3 meters. x3 equals 6 meters. And x4 equals -3 meters. All right, so if we look at a number line, or let's look at our axis. Well, let's say this point represents 0. 1, let's go -1. -2, -3, -4, -5, so on and so forth. Right, so mass 1 would be located here. That's 30 kilograms. Mass 2 would be located here at 5 kilograms. Mass 3 would be located here at 10 kilograms. And mass 4 would be located here at 15 kilograms. All right, so we need to find center of mass. So first, let's calculate the moment of the system. All right, so that'd be the sum from I equals 1 to 4 of m sub I times x sub I, right? So we get -2 times 30, which is negative 60 kilogram meters. Plus 15 kilogram meters. Plus 60 kilogram meters. Then minus 45 kilogram meters. So the moment is negative 30 kilogram meters. We also want total mass. Next, right? So that is the sum I equals 1 to 4 of m sub I. All right, so 30 kilograms plus 5 kilograms plus 10 kilograms plus 15 kilograms, which is 60 kilograms. Using that then, center of mass is negative 30 kilogram meters divided by 60 kilogram meters. So this is negative 1/2, I'm sorry, 60 kilograms, right? This is negative 1/2 meter. So negative 0.5 meters is our center of mass. So if we were to plot that using red, let's say, that's x bar. We now look at point masses in the plane. Right, so we're going to generalize this now for a two-dimensional coordinate system. Well, let's go ahead and take a look at just a single point mass. Call it M1. Located at a point Y1, X1. Well, clearly, this is going to have a moment with respect to the x-axis, right? And a moment with respect to the y-axis. The x moment, which is denoted m sub x, right, would be the mass times the distance from the x-axis, which would be y1, right? Right, so mass times the distance from the x-axis. Then we have the y moment, denoted as m sub y. This would be the mass times the distance from the from the y-axis, right? Well, its distance from the y-axis is x1. Now, moments are additive. So if we have several point masses, we get the x moment, mx, right, is the sum of all the x moments. So I equals 1 to n, m sub I times y sub I. Likewise, the y moment of the system, m sub y, right, would be the sum I equals 1 to n of m sub I times x sub I. And again, total mass of the system, represented capital M, would just be the sum I equals 1 to n of just mi, right, the sum of all the masses. Well, x bar. Right, so we're going to call it the x coordinate of the center of mass. Is the x moment of the system I'm sorry, it's the y moment of the system divided by total mass the y-coordinate of center of mass would be the x moment of the system divided by total mass of the system. All right, so mathematically, x bar is m sub y over m, right, which is the sum I equals 1 to n of m sub I times x sub I, all over the sum I equals 1 to n of m sub I. Y bar is mx all over m, so sum from I equals 1 to n of mi yi all over sum from I equals 1 to n of mi, and then our actual center of mass itself is the ordered pair x bar, y bar. And so say M1 is 2 kilograms, M2 is 6 kilograms, M3 is 4 kilograms. These are our 3-point masses. I'm going to call R1 the point where the first mass is located, so that's at negative 1, 3. Let's say R2 is at 1, 1, and then R3 is at, or M3 is at 2, negative 2. Right, we want to find the center of mass. Well, first we need to find the x moment. And so remember, that's the sum I equals 1 now to 3, m sub I, y sub I. So we get 2 times 3, we get 6. I'm going to assume meters. Plus 6 kilogram meter plus negative 8 kilogram meter. So the x moment is 4 kilogram meters. Y moment. Sum I equals 1 to 3. M sub I, x sub I. So negative 2 kilogram meter plus 6 kilogram meter plus 8 kilogram meter. We get 12 kilogram meter for the y moment. And total mass. All right, 2 kilograms plus 6 kilograms plus 4 kilograms is 12 kilograms. So using those, x bar, 12 kilogram meters divided by 12 kilograms. So we get a location of 1 meter. Y bar would be 4 kilogram meter divided by 12 kilograms. So we get a third meter. So center of mass is the point 1, 1/3. We now consider a region under a curve. Right, so this is typically defines a lamina. Right, so all a lamina is a thin sheet of material. And we refer to the center of mass of a lamina as a centroid. Right. So let's now look at a lamina. Right, so there's our coordinate axis. Let's say there is our function y equals f of x. So for the region, let's say it is this. Right, so it's going to go from A to B. Right, so we consider this region to be our lamina. Right, so call that region R. Right, so we need to find 3 things, right? We need to find the mass of the lamina. We need to find the 2 moments of the lamina. Well, mass is simply the mass density times the area, right? So what we do is we say, okay, well, let's assume this has constant mass density. Call it rho. Then we would have the mass is rho times the area. Well, area is an integral, right? Integral from a to b of f of x dx. And I want more room, so I'm going to rewrite that down here. Not equals times so there's our mass. We now want to look for the laminas, or the moments rather. So to do this, let P be a regular partition of our interval a to b. Right, since we can choose any sample point we want, what we're going to do is we're going to choose the x-coordinate of the centroid of the rectangle for the interval xi minus 1 to xi. I.e., we're saying that xi star is the centroid for the rectangle. Well, the x-coordinate for the centroid, rather. Well, for a rectangle, that's just going to be the midpoint. So it's going to be xi minus 1 plus xi all over 2. This means we construct the rectangle to have height f of x sub I star. Meaning that the y-coordinate of the centroid is the point that divides the rectangle in half. So it's f of xi star over 2. Therefore, the centroid for the ith rectangle is the point xi star f of xi star over 2. Now, treating the rectangle as a point mass at the centroid will not change the moment. So, the moment of the rectangle with respect to the x-axis is the mass of the rectangle times the distance the centroid is from the x-axis. In other words, this is the x moment. It is rho times the area, which is f of xi star times delta xi, then times the distance from the x-axis, which is f of xi star over 2. Simplifying this, we get rho over 2 times f of xi star squared times delta xi. The y moment is similar. And it is again the mass times distance the centroid is from the y-axis. Mass is rho times area, which is f xi star times delta xi, then times the distance from the y-axis, which is xi star. Simplifying, we get rho xi star times f of xi star times delta xi. Right, remember moments are additive, so total moment for the lamina, total x moment, right, would be mx, which can be approximated as the sum I equals 1 to n of rho over 2 times f of xi star squared times delta x sub I. Y moment for the lamina can be approximated as the sum, I equals 1 to n, rho xi star, f of xi star, times delta xi. Taking n to infinity, we get that the x moment for the lamina, rho over 2 times the integral from a to b, f of x squared dx, and m sub y, the y moment, rho times the integral from a to b, x times f of x. If we take these with the mass, we get center of mass, right? So we still have that x bar is the y moment divided by mass. Y bar is the x moment divided by mass. We're going to find the centroid of region with a constant mass density, rho, between f of x equals e to the x, the x-axis, and the lines x equals 1 and x equals 3. So, in other words, if we take a look at a rough sketch, again, not drawn to scale, the region we're looking at is this region. And so that's our lamina. So the first thing we need to do is find mass. Right, so total mass, rho times the integral from 1 to 3, e to the x dx. Right, so that's rho e to the x from x equals 1 to 3, which equals rho times e cubed minus e. Right? For the x moment, rho over 2, integral from 1 to 3 of e to the x squared dx. Right, so that's rho over 2, integral 1 to 3 of e to the 2x dx, which is rho over 4 e to the 2x evaluated from 1 to 3. So rho over 4 times e to the 6th minus e squared. And finally, the y moment. Rho times the integral from 1 to 3 x e to the x dx. Right, this equals rho times the quantity x minus 1 times e to the x evaluated from 1 to 3. So it's rho times 2e cubed minus 0. So 2 rho e cubed. This now allows us to find x bar and y bar, right? X bar is the y moment divided by mass. So we get 2 rho e cubed over rho times e cubed minus e. We can cancel out the rows. We're left with 2e cubed over e times e squared minus 1. This leaves us with 2e squared over e squared minus 1. For y bar, it's the x moment divided by mass. Right, x moment was rho over 4 times e to the 6th minus e squared over mass, which was rho times e cubed minus e. Right? Rows will cancel out. We can factor out an e squared from the numerator. Be left with e to the 4th minus 1 over 4e e squared minus 1. Right? E's are going to cancel. We're left with a single e in the numerator. E to the 4th minus 1 is a difference of squares. And so what this simplifies down to is e squared plus 1 all over 4, or e cubed plus e over 4. Therefore, the centroid two e squared over e squared minus 1, e cubed plus e over 4. If our lamina is a region between two curves, so let's say something, I don't know, something like this. from A to B. Okay, so we say this is the region. All right, so that's our lamina. It is a fairly straightforward exercise to show that the mass is the density times the integral from A to B of f of x minus g of x dx. I did forget to put up here that this is mass density rho. The x moment is rho over 2 times the integral from A to B f of x squared minus g of x squared. And then the y moment would be rho times the integral from A to B x times f of x minus g of x dx. We will find the centroid of the region bounded above by f of x equals 1 minus x squared, and below by g of x equals x minus 1. Well, the first thing we need to do is determine our interval, so we need points of intersection. So we set f of x equal to g of x. We get 1 minus x squared is equal to x minus 1. So x squared plus x minus 2 is 0. And it is a fairly straightforward exercise to show that as a solution, we get x's either negative 2 or 1. Now, the previous example showed that the rho doesn't matter, right? The rho's canceled out. So without loss of generality, we can take rho to just be 1, right? We can take it to be unitary. The mass would then be the integral, negative 2 to 1, of f of x minus g of x. So negative x squared minus x plus 2 dx. So when we evaluate this out, we get 9/2. X moment will be the integral from negative 2 to 1, f of x squared minus g of x squared. And it should be a half that, right? So 1/2 the integral from negative 2 to 1. 1 minus 2x squared plus x to the 4th minus x squared plus 2x minus 1 dx. And so we get 1/2 times the integral from negative 2 to 1. X to the 4th minus 3x squared plus 2x. And when we evaluate this out, we get negative 27 over 10. Finally, the y moment. Be the integral, negative 2 to 1 of x times f of x minus g of x. So the integral from negative 2 to 1, negative x cubed minus x squared plus 2x. And when we evaluate this out, we get negative 9/4. So x bar, my over m, negative 9/4 over 9/2, which equals negative 1/2. Y bar, negative 27 over 10 over 9/2. This is negative 3/5. So our centroid is negative 1/2, negative 3/5.